So it's
Sayantan.
Sayantan?
Sayantan, yes.
Sayantan Roy.
Okay.
Okay. So let's think everything is set up. Okay, I guess we can start. So now today we will hear a talk by Sayantan Roy about abstract model structures and compactness theorems. Please.
Am I audible? Yeah. So thank you, sir, for inviting me to this presentation, and special thanks also goes to Vitali sir for suggesting that for giving me the suggestion that I presented here. So today I'm going to talk about some abstract versions of compactness theorems, and this, as you can see, is a joint work with Shankar sir and Nihir sir, both of whom are my former PhD thesis advisors. So I will begin with the outline for the talk. So I will first start with some historical remarks, and then I will move on to the motivation.
Уважаемые организаторы, простите, в Zoom видно аудиторию, но не видно ни докладчика, ни слайдов.
Okay, so sorry, we forget to
Share the screen.
to share the screen. Yes, thank you. Yes, sorry for that. Okay. Okay. Is it okay now?
Yes, okay. We can see the slides in Zoom.
Sorry.
Okay, so as I was saying, so I will just start with the outline for the talk, and I'll begin with some historical remarks, and then some motivation, which led to the genesis of this paper, and then I will introduce some technical preliminaries, talk about a special kind of abstract model structure, which is one of the key concepts, and the normal abstract model structure and compactness theorem related to it. In this context, I will discuss three types of compactness: the Henkin-style, the topological ones, and finally the proofs using ultrproducts, which essentially boils down to a corollary of ВШЭ theorem. And if time permits, then I will talk about finiteness and compactness, its relation with compactness. I will conclude the talk by pointing some future directions and open problems. Okay. So here goes. So the field of logic has grown phenomenally since the turn of the 20th century. This might at least be due to the involvement of mathematics and computer science with logic, which is still continuing. There is also an unprecedented upsurge in the number of logical systems, by which I mean concrete logical systems, and which continues even to the present day, making it practically impossible to even have an idea of all branches of the subjects. However, from a conceptual perspective, it is really necessary to have a bird's eye view of the subject for general patterns that will otherwise remain buried deep under the heap of particularities. Several such attempts have been made in the history of logic, even in the history of mathematics also. For example, if you think about the category theory, abstraction of groups, fields, universal algebra, these all are motivated by certain kind of abstractions that try to unify the particularities that is otherwise seems like disconnected, heap. And so the first progress towards this direction was made by Paul Hertz in 1921 by the notion of SAT system. So as Arnold Koestler writes, Hertz intended the inquiry to be very general, and as a result, he deliberately treated the sentences, these are expressions of the form, which is very similar to the sequence nowadays, as composed of elements that are not assumed to have any special logical form. Essentially, Hertz is talking about the structural rules which is now known as structural rules. The logical complexity of the elements was deliberately omitted, for that would have diminished the scope of generality. Later on, his work was extended further by Gerhard Gentzen and Arnold Koestler. Now, there is a difference between the works of Gentzen and Koestler. I think Gentzen extended Hart's work in the sense that he also considered the complex logical rules and others, whereas in Koestler's work it's purely structural, mostly structural. Okay. So at around the same time, Alfred Tarski developed a similar abstract approach to the study of logic via the notion of consequence operators. In this work, Tarski's aim was to provide an outline of the general framework for the methodology of deductive sciences. Essentially, Tarski was dealing with structures of this particular form, a turnstile, where L is a countable set and turnstile satisfies certain property, by which I mean like reflexivity, monotonicity, transitivity, and finiteness. Tarski originally also assumed finiteness, but later this condition was dropped. Anyway, here also notice that the nature of objects is not specified. He simply dealt with a countable set, no structure, nothing, just elements. Even though Tarski himself called these objects meaningful sentences, but this is just a terminology, suggested terminology, nothing, the formal result is not dependent. Okay. Tarski's idea was investigated in great detail by Polish logicians such as Lindenbaum, Bohr, Shusko, Wojcicki, and so on. In the hands of this logician, the theory of consequence operator took an algebraic turn. So they considered pairs of this particular form, but here A was an absolutely free algebra, unlike in Tarski's case, which considered only sets, even though it was countable set. There was also another development that in this the cardinality restriction was dropped. And again, this turnstile satisfies certain properties, so they dropped the finiteness, which means that in this case, turnstile satisfies reflexivity, monotonicity, transitivity, and something that was introduced by Bosch and Shusko, I think, that is called structurality axiom. So the notions of structural consequence operator and hence sentential logic was subsequently introduced. And the generalization of these notions of sentential logic under the name of abstract logic were also investigated by Shusko and his co-authors. Nowadays, this line of research is pursued under the scope of abstract algebraic logic. Okay, the modern notion of universal logic, introduced by Professor Jean-Yves Béjou with the aim of developing a general theory of logic in the same way as universal algebra, is a general study of algebraic structures. It can be seen as an extension of the same ideas and spirit. So Professor Béjou's original proposal was to focus on the pairs of the same form where L turnstile, where L is just a set and turnstile is just a relation of P L cross L. So here no properties is assumed and no cardinality restriction also. So L need not be an algebra as in more traditional cases. However, in later years, approaches based on other mathematical theories, for example, category theory, have also been considered. All these are part of universal logic project. Now, when I talk about category theory, I should also mention the main focus of the talk, which is distinct from the approaches to category theory. So, in category theory, there is a well-developed field called institution-independent model theory, which also deals with certain abstract kinds of model theory independent of the syntax. However, here we do not go into that category theory, primarily because it was our feeling that in approaches to category theory, the concepts becomes quickly so involved that it's become very difficult to lose track of them. So we keep it simple, we just deal with ordinary set theory. And so this is the motivation. So the compactness theorem for a logic states roughly that the satisfiability of a set of well-formed formulas can be determined from the satisfiability of its finite subsets and vice versa. For a given logic, the proofs of this theorem usually depend on the syntactic and semantic particularities of the corresponding unit. I think that is what we feel when we see the presentations of the compactness theorem. However, a deeper analysis of the statements itself of compactness theorems for various logic show that one can develop a generalized notion of compactness independent of these particularities. This talk is aimed at developing the theory of one such generalized notion of compactness for a particular class of structure, which I have told normal abstract model structures. Okay. So although in essence our results may be said to belong to the subject known as abstract model theory in the sense of Barrois and his co-authors, they lack the strong commitment to the conventional concrete systems of logic that are characteristic features of works in this theory. For example, they mostly work with first order logic and their extensions and so on, but there is no first order logic here. Instead, the results in this talk may be compared with those of institution-independent model theory, of which I have already mentioned. Although in contrast to the category theoretic approach pursued there, our approach is set-theoretic, our results are also independent of precise notions of concrete models, sentences, satisfaction, and so on. Thus, the spirit of this paper is similar to that of universal model theory in the following sense. So, universal model theory is part of the grand project of universal logic promoted by Beju and others. Like universal logic in general, universal model theory in particular is not seeking for one single model theory in which all other model theories can be expressed. The universal model theory idea, on the contrary, means providing a mathematical framework for developing model theoretic concepts and result in a non-essentialist and groundless manner, and which may be reflected at the level of actual logics in the form of concrete model theories. So it kind of gives you a schema of developing model theories. Here by non-essentialist we mean the absence of a lasting individual essence of anything in general, which means, for example, if you ask what are formulas, it does not give an answer, because these are just elements of set, that's all. And of logics and logical theories in particular, and by groundless we mean a true absence of commitment to actual logical strength. This is very important because this is where the institution-independent model theory differs drastically from abstract model theory based approaches, because these are mostly on concrete logical theory. Here it is not. Okay, so let me just start with some basics. This is, I mean, I will also mention some basics because this is just mostly to make sure that you are on the same page. So we'll just, and no example will go beyond classical proposition. So yeah, so set, consider the classical proposition. LCP here denotes a set of all well-formed formulas of classical propositional logic. Here a set of, we know that a set, I mean, we say that a set of formulas is satisfiable if there exists a valuation that satisfies it. It is said to be finitely satisfiable if every finite subset of gamma is satisfiable. Compactness for classical propositionality says that finite satisfiability is equivalent to satisfiability. Now let us ask some pertinent questions. Does the statement of compactness theorem depend on the syntax of set-theoretic? Well, yes and no. Yes, in a trivial sense, because it is after all about classical propositional logic. It should depend on the syntax of classical propositional logic. No, in a deeper sense, because it only talks about equivalence of satisfiability and finite satisfiability.
Excuse me.
Yes.
What does CPL refer to?
Sorry?
CPL.
This is a classical propositional logic.
Classical predicate logic.
Oh, okay.
Yeah. Same question you can ask for the semantics. Does the statement of compactness theorem depend on the semantics? Same question you can ask for the semantics. Does the statement of compactness theorem depend on the semantics?
Can you repeat the question if there is one? No, please carry on.
Can you repeat the question?
Okay. Yes, well, yeah. If you have a question, please write in the chat. In chat, yes, please. Okay.
Okay, so again we ask the same question for the semantics of set. Again here the answer is both yes and no. Yes, in a less trivial sense, because when you prove compactness theorem, we do have a concrete semantics. No, in a more general sense, because the semantics, the traditional semantics is not the only one that we will deal with. So the compactness theorem also makes sense for a different semantics. Okay, then the question, this is, I mean, characteristic feature of universal logic approaches. What theoretical minimum is required to make sense of compactness theorem for any logic? Now, if you want to make sense of this, of course, you need to know what logic means, and also you have to decide the theoretical minimum. Okay, of course, you will need a set of formulas, that's the basic requirement, and you will need a set of models, and you would need an way to make sense a given set of formulas. For now, I'm not referring this is just quote, a definition of the phrase that gamma is satisfiable. Because if you have gamma is satisfiable, then you will simply say that the finite satisfiable defined as if every finite subset of gamma is satisfiable. So finite satisfiability derived definition from satisfiability. So this is the theoretical meaning that you get. Okay, so this is now going to the technical preliminaries. So this is the definition, official definition of abstract model structures. It's a triple of this form where M and L are sets. PL denotes the power set of L, and this double tungsten is a subset of M cross PL. So if this pair M gamma belongs to this double tungsten, you simply write it in fixed notation in,
Yes.
and you say that it's satisfied.
But satisfiability, what is satisfiability here?
Exactly. So even though I say that M satisfies gamma, this is called, I mean, we say that gamma is satisfiable if there exists a model M that satisfies gamma. I will come to the definitions. But the point here is that
It's not quite clear because this small m, it is taken from where?
just an arbitrary set.
It's not from big M, it's something else.
No, it's from big M because
From
this
big M. Ah,
this is a subset of M cross PL.
I see.
So we have a class of all possible models. Right?
Yes, so I'm coming to that. For the definition to make understanding, you can think of the elements of M as models, the elements of L as formulas, but this is strictly not necessary.
Okay.
I mean,
The formulas are in, I see, yeah, thank you.
yeah. So, and then we say that M satisfies, that's all. Fine. Okay. So, this abstract model structure, they give rise to, I mean, these structures, they give rise to the abstract model structures in a very natural way. We have worked out the details. Just notice that the choose spaces formulation to this gives a variety of examples. And what is quite interesting is that categories, modular solution, they also give rise to MST in a quite non-trivial way. It was the most hardest example that I had to come up. And the notion of functors between categories, they relate to the more, I mean, more nuanced notion of, I mean, you can see this as structure preserving maps if you just define the structure preserving maps between abstract models in a very natural way. There is a function gf, g takes m2 and some m prime, and then so on. And this is very natural to do this. But we have not done this, we are working on this later. Okay. So here now satisfiability. So if you have suppose that this you have an MST and gamma is a set of formulas. I have to say this, but nevertheless this is not this. So I will refer to the elements of M as models, but again I will just reiterate this. There is no such commitment that I am making here. Okay, then gamma is said to be satisfiable if there exists a model that satisfies gamma. It is finitely satisfiable if every finite subset of gamma is satisfiable.
But do you need a requirement that if gamma is satisfiable, then every its subset is satisfiable?
Well, that's precisely normality.
But this is not postulated.
This is not postulated because this is the general notion of satisfiability. We'll come to the notion of normal abstract model structure, and there we have this requirement that M satisfies gamma if and only if every element of gamma is satisfied. So that's the specific requirement. Because I mean the model theory that is normally familiar, they satisfy the requirement, but some esoteric model theory they may not satisfy. So it was aimed towards maximal generality. Anyway, yeah. So a compact abstract model structures are those for which satisfiability and finite satisfiability goes pretty naturally. Okay, the compactness problem then is find necessary and sufficient conditions for an AMST to be compact. So this is the problem that is the central focus of this talk, and we are going to investigate this for this normal abstract model structures and discuss issues with, discuss compactness of this particular structures. So normal abstract model structure, as was already guessed, it is said to be normal if gamma is satisfiable, if and only if every element of gamma is satisfiable. Exactly.
Yes.
So this is the more traditional.
Exactly.
That's why I call it normal. Yeah.
So you don't need non-normal.
Yeah, exactly. So, okay, now you define the mod function, which is essentially the set of models that is set satisfies. Now, notice here that actually for general AMST, the definition in the paper was, I think, the mod gamma is equal to set of all models M so that M satisfies gamma. However, due to normality, it is enough to define M satisfies this singleton, every element of gamma. And similarly, you can define the dual function, the theory function, which for every subset of subset of models, you define it to be the set of all formulas that is satisfied by every model in that subset. That's the theory. And now we go into the different groups of compactness theorem. First, we discuss the Henkin-style, then topological, and then proofs using ultraproducts, which essentially, as I said, boils down to ВШЭ theorem. Okay. So I'll just very quickly just go with the structure of this proofs of using Henkin-style proofs. So you consider CPL and classical proposition logic, and you take a finitely satisfiable subset of the classical proposition, let's call it gamma. Then the traditional presentation is essentially does this. So you fix the enumeration of classical, the formulas, and then you construct a following sequence of sets, which you add. You just start with gamma as your initial set, and then you define sigma n plus 1 as sigma n union this phi if this is satisfiable, otherwise you keep it as it is. And then you take the union of this. Final step is to show that sigma is maximal satisfiable. Now it's very interesting to know that this is actually equivalent to compactness for normal limits. However, we need to assume that L is not satisfied. If L is satisfiable, then due to normality every set is satisfied. So that's not a very interesting case. So if you have a normal MST, then these two conditions are equivalent. In fact, in order to prove 2, the only part that is non-trivial, that uses normality, is the fact that, so basically if you want to prove 2, you would extend a finite satisfied to a maximal finitely satisfied, which is done by Zorn's law. But in order to show that maximal finitely satisfied it actually satisfiable, you need the normality. So the theorem for maximal finitely holds for every MST, but this MST means abstract model structures, but this is requires normality. And these are some, these are some other results that we come up with, and there are more, but it would be crammed if I put too much in a slide. So yeah. Now the topological proofs. So I will very briefly mention the definition of topological, just to again say that we are on the same page. So a topological space is a pair x tau where x is a set and tau is a collection of subsets. These are called the open subsets, such that the empty set and the whole set is belong to tau, and tau is closed under arbitrary union and finite intersection of open sets. Okay, and the cover, if you have a topological space x tau and take a subset of x and a set of subsets of x, say gamma, then we say that gamma covers y if the union of every element in gamma, this contains y. It is said to be an open cover if every element of gamma is actually open. Compact topological spaces are those for which every open cover has a finite subcover. Now, it is interesting that when we are dealing with this compact topological space, I was not aware of all the proofs, so I am actually very indebted to one paper. I think this is by Alexander Pazou, I think, if I am not pronouncing it correctly. So he gives a list of proofs, and this paper was modeled only after that. So even the section names were almost copied. So, but the point was that, like, the moment you see that every open cover has a finite subcover, if you think of this open cover as satisfiability, you already see that satisfiability has a finite. Satisfiability implies finite satisfiability, and the only other thing is to imply that the other version. So the link between topological intuition and compact topological space and other things is pretty natural. So essentially, for a given logic, the argument of these types of proofs can be broken in the following steps. First, you construct a topological space from the logic under consideration. Then prove the compactness theorem for the logic holds if and only if the associated topological space is compact. And finally show that the topological space is indeed compact. For example, in the case of classical proposition logic, the corresponding MST is this, where this 2 to the power LPC denotes the set of all valuations, and LPC denotes the set of all well-formed formulas of classical propositional logic. And for every V, this V satisfies gamma if and only if every element of V evaluates to 1. Every element of gamma evaluates to 1. Now we do the following steps. You consider the topology generated by this models of negation alpha, as the base. It is compact by Tychonoff theories. I have just written it, but there is slight non-triviality. You need to map it to homomorphic to some homomorphic set, and then you get the compactness theory.
Excuse me. Now we are talking about propositional logic.
Classical proposition. So all the examples are classical proposition. So CPL, wherever it comes, it's classical proposition.
Proposition. Oh, I see.
And then you simply say that gamma is not satisfiable. You prove these equivalences. You show that gamma is not satisfiable if and only gamma is not finitely satisfiable. At this stage, at this step, you actually use compactness. So gamma. So yes, that is more or less the structure of the proof. If you just repeat this argument more or less to the abstract model structures, you get that the same thing. Here, the idea earlier the topology was generated by mod alpha taken as a base. Here, notice that in classical probability it is actually equal to v in 2 to the power this thing minus mod alpha. So in the general case, you do not have 2 to the power LPC, you have m. You take this, and this is precisely what is particularizes to the example. But the only difference here is that earlier this was taken as base. Here this should be taken as subbase, and you have to use Alexander subbase theorem to get this equivalence. Okay, so this and then moving on to the ultraproduct proofs. So this above theorems, these characterizations, I mean the two equivalence of compactness, they give necessary and sufficient conditions for a normal MST to be compact. However, in order to show sometimes that a finitely satisfiable set gamma is actually satisfiable, one may wish to construct a model satisfying gamma using the models which satisfy the finite subsets of the set. These theorems give us no clue about how, if at all, we can achieve this goal. Walsh's theorem gives us a new perspective regarding this issue. A similar line of investigation is pursued here. The main tool in the following study is that of ultralimits, introduced by Bernstein in 1970 for ultrafilters over countable ordinal, and later extended in 1978 by Sachs for ultrafilters over arbitrary cuttings. The presentation of this, however, does not depend on the paper. They depend on this Isaac Goldwyn's paper and book, Ultrafilters to Over Matters, because he does not mention anything about current, just talks about arbitrary sets. Okay, so here again some basics for filters. So given a set I, a filter on I is a set satisfying the following properties. So if both x and y belong to F, then their intersection also belongs to F, which is the downward derivative property. And it is also upclosed in the sense that if x belongs to the filter, then anything that is up above x also belongs to the filter. A filter is said to be proper if empty set does not belong to the filter, and an ultrafilter is a maximum proper filter on I. Okay. Now the new definition of ultralimit. So if you have a topological space x tau and let xi be a sequence from x and v is an ultrafilter on I. An element is of x is said to be an ultralimit of this sequence in x relative to the ultrafilter v if for every open set containing x, the set of all indexes such that xi belongs to open set u, this set belongs to the ultrafilter v. In this case, we simply say that xi converges to x in the topological space related to the ultrafilter. Okay, if for every ultrafilter v on I, every sequence converges in the topological space relative to the ultrafilter, then we simply say that x tau is ultralimit complete relative to I. And if you apply this definition to the, so here is the condition. So we have already defined the topological space where we have proved the compactness, and then the topological space, I mean this considering to every normal MST you have a topological space and you consider the ultralimits inside the topological space. Give the name ultramodels. That's the basic idea. So you have a normal MST and consider this topological space which we have defined earlier. An element U is said to be ultra model of a sequence of models here from M relative to the ultrafilter V if V is an ultrafilter on I and U is an ultra limit of this sequence relative to V. Examples like, for example, ultraproduct is one example, but here is a more basic example. So again, consider the topological space that we have defined earlier. So you have a sequence of valuations from the LPC set of functions and an ultrafilter V. The ultra model of this sequence of valuation relative to V is this valuation. So there is a typo, it should be capital I. This is well defined because V is an ultrafilter. So is it either belongs or its complement belongs to this. So this is now known as, I mean, this is called, I think this was called ultra valuation in one papers, and someone's, it was studied in great detail, but the idea itself, even though it was published like 2023 or 24, the idea itself I think is very, it's older, it's just folklore more or less. So again, one example of ultra model is ultra valuation, another is ultra product. Okay, so just please let me know if I am going, if I still have time, just yeah. So yeah, okay. So this is the characterization of ultra models. Now you see that whenever I am talking about ultra models, it does not have any structure like ultra models. It's just an element of model, and this is one of the main reason we pursued this approach. So you have a normal MST and you consider the topological space again. You have a sequence of models as before. V is an ultrafilter of I and this U is an element of N. Then U is an ultra limit of this sequence of model, that is U is an ultra model. If for every sigma, the set of all indexes such that Mi satisfies sigma, this belongs to the ultrafilter, implies that the ultra model satisfies sigma. So what is the importance of this theorem? It essentially gives the non-topological characterization of the ultra models. And also notice that this is one direction of ВШЭ's theorem, if you just replace ultra models by ultra product. So what about the other direction? But it is interesting that even in ВШЭ's theorem you have both directions, but this one direction is enough to give you compactness theorem for normal limits. So this is our third criterion of compactness theorem. So okay, so here you have a normal MST and the topological space is defined as previously. Just the only new notation is fin set sigma, which denotes the set of all finite subsets of sigma. Then M is compact if and only for every finitely satisfiable sigma, M tau n is ultra limit complete with respect to fin set sigma. So you just take a particular kind of set. So this is essentially what we do, just the indexing is need to be careful. So the one direction was given, now for the other direction. So we had this direction, and there is also something if you just tinker with the topological space here, instead of topological considering M minus mod alpha, you consider mod gamma and consider this as the basis for the topological space. And then if you have the topological space, then U is an ultra limit in the new topological space related to V every ultrafilter if and only if for every sigma U satisfies sigma implies that the set of all indexes such that Mi satisfies sigma belongs to V. And if you combine this theorem, two theorems, you get what I refer to as generalized ВШЭ theorem, because this is precisely the form of ВШЭ's theorem if U is the ultraproduct. Okay, I think I'm just at the last segment of this talk, and
maybe it's
sorry,
too quick. Yeah, you.
Oh, I need to. Oh, sorry, I need to. Sorry, So here.
You have like 30 minutes.
Oh my God. I think this is the last. Okay,
But we will have some questions.
Yes, that would be great.
So take most of the time.
Yes, please.
Can you go back one slide?
Sure, please. One slide?
Why does this? No, the next one.
The next one?
So when you define a base for the topology, why is it like correct? So why does every intersection well there is a criterion for a set of subsets to be a correct base, and why is it like fulfilled in satisfied in this case?
So in this case, in this topological case, so basically here you can, so that is the normality condition. Here models alpha is equal to intersections of mod singleton alpha, so where alpha belongs to. So that is used to give this.
So what the criterion for basis, if it's for any two elements, the intersection should...
for any element of the intersection, there should be an element of the base that
is the subset of the intersection, right? Yes. So here, so if we have two gammas, let's say gamma 1 and gamma 2, then what is
the union, gamma 1 union gamma 2, this is equal to...
This is the intersection.
This is precisely equal to mod gamma 1 intersection mod gamma 2. Because you just take the intersection of every element.
Okay.
Yes. Okay.
So, yeah. So that's why, I mean, the normality is important. You need both directions. One direction would not suffice. One direction would suffice for...
And normality gives this, because normality means that the satisfiability means that all formulas should be...
Right. You would get subset if you consider one direction. I mean, I think you can figure it out, but I have not explored this, so this is...
Okay. And if you don't have normality, then it's not necessarily the base, right?
No, if you don't have normality, then I don't think you would have a dual characterization this easily, because the characterization depends on this being a topological space. I'm not sure if you first of all, of course, one can introduce more general structures than topological space, but I'm not sure whether they will give. The other thing would be to consider this as a sub-base rather than a base. But again, I'm not sure how this equivalences will be preserved there. Because one of the motivation for me was to, this part at least was to prove some general form of Bosch's theorem, from which compactness will follow. So we needed this two criteria. So basically, I mean, the structure was that when I came to the topological proof was done, then I thought that okay, fine, we have a topological space. Why not consider ultra limits? And the ultra limits were just specially termed arbitrary as ultra models. That's all. Repeating natural terminology, because ultra valuations, ultra models. That's all. And then when we had them, then we find that okay, so this talk of topology is something that's burdening. I mean, you always need the definition of ultra limit is nothing but trivial. So what if you can give some easier criteria? And this was the when we got the earlier easier criteria from the okay, this is Bosch's theorem 1/2. What about the other half? And then this criteria. Okay. Any questions? Okay.
Not at this point.
No. Okay. Okay. Fine. So this is Bosch's theorem. I just forgot to mention that in the case of first order logic, you have a proof of compactness using Bosch's theorem. Here also you can do the same, but the notation and technique is pretty complicated, so I omitted it here.
So V is an ultra filter on what?
V is an ultra filter on the index set.
U is no.
No. V, so basically
U.
So this is a V ultra limit, which means you have an index set, you have a sequence of models mi, and then so basically, for example, I did not mention the model. So you have a sequence of models mi here, which got omitted here for some reason, and then V is an ultra filter on the index set I.
On the set of indices. Okay. And U is an ultra filter on this?
No, U is an element of M.
Limit of the sequence.
U is an ultra limit
Under this ultra.
under this ultra. So I'll just go back to the definition then.
Yes, ultra limit. It's defined from there.
Yes.
Ultra limit. Okay.
Ultra limit. Here, if you just take the topological space introduced by this, then you get the ultra limit is called ultra limit.
Okay.
So yes. So yeah. So okay. So this talk was presented at a conference, and after the conference, there was one professor who came and then said the compactness. So in literature, there are some papers who actually define finiteness as compactness, and there is a mix of this. So he asked me, so what about the notion of finiteness? They look very similar, but can you give some semantic criteria for finiteness? And then this gives rise to this, the extension. This is not in the paper, in this paper from which this major.
Yes, it's also called compactness sometimes.
Yes, exactly. But it's very useful to distinguish between this, because compactness is essentially about satisfiability. Finiteness is all about, not all about, a lot about deduction. The intuition comes from deduction, a lot of intuition comes from. So a logical structure is finitary if gamma entails alpha, implies that there is some finite subset that also entails alpha. Okay, now there is a new notion, model theoretic logic. So the term is actually taken from Professor Yuko Vananen's work, who also works on this model theoretic logic, but the definition is different. So if you have a model structure, abstract model structure, then the logical structure induced by M is this particular logical structure, where gamma entails alpha in the induced structure, if and only for every M satisfies gamma implies that M satisfies alpha. This is more or less the standard definition. But the important point to note here is that
it's called logical consequence.
It's exactly logical consequence. Here, even though I have used the definite article da, the logical structure induced by M, there are many ways, multiple ways to define logical structures. For example, you can say that, we are working on a paper currently where we are just investigating different things. If for all M, such that M satisfying gamma, there exists a model N such that M satisfies alpha. This is also a valid way of inducing a logical structure. So there could be relationship, and these are nice properties. So a logical structure is model theoretic if there exists a model such that the induced logical structure is same as the model logical structure. Okay. So this is the characterization. So you have an MST. So note that this is for arbitrary MST. So you have an MST, and this is the logical structure induced by M. Then the logical structure induced is finitary if and only if for every alpha this particular abstract model structure is compact. So basically, if you have a negation, this simply means that the models of classical negation, if you take the models, if you just take the families of models of negation, each of them is compact, implies that this is finite. And a rather surprising consequence of this is the following theorem, which states that if you have an MST that is finitary, such that induced structure is finitary, if there exists a singleton unsatisfiable set, then M is compact. This is surprising because now suppose you have the compactness theorem for first order logic. You know that this is finitary. And then there exists a singleton satisfiable set, which is again obvious. So the compactness theorem immediately follows from the compactness theorem. And the compactness theorem also immediately follows if you have a semantically defined logical structures which is exclusive. So basically you just need one unsatisfiable set, and that's all. Okay, so yes, now the future.
Does singleton in this context mean like a set that consists of one element?
No. I'll just say what I want to say. So it means that like if in the logic there exists a singleton satisfier, like some alpha.
So like a singleton set is a set that contains a single element?
Yes, exactly.
Okay. So why why do we need a restriction like this?
Okay, so just put here, if you just have a singleton, so if this is trivial, and if there is nothing that is satisfying this, so you get the full model.
Yeah.
And then you have here n. So what this says, for every alpha this is compact. Now if this is empty, then you say that for that particular alpha, this m turnstile PL is compact, which is giving you the original model structure is compact.
Yeah, okay.
So this is just
Am I right that this corollary says that compactness follows from completeness? That this is quite.
Yes, compactness follows from completeness, but the other thing is also, I mean, if you have completeness, then you basically have a lot of information. But the importance of the result is more lies in the logic that is defined semantically first. So normally if you have this logic which is defined syntactically, and you have an axiom and things, then you prove completeness. From this, if it is finitary compactness, I mean this theorem does not add much. But it is important if the logic is defined semantically. For example, as far as I know, the Bogverse logic and other logic, these were defined semantically first. So
which one?
Bogverse logic. The three-valued logic of Bogverse logic. I'm not if I'm sure pronouncing it correctly. But okay, the general point is that there are logics for which the semantics is defined first. And then you talk about then you come to the axiomatization and other things. For those logics, this will be very useful. Because if you know if you know the semantics, so this is essentially talking about adequacy. I mean, which is what completeness, soundness and completeness. Only completeness would not suffice, of course, is soundness. But yeah, that's the main point. Okay. Yeah, so yeah, several other proofs of compactness can be found in the literature. For example, here I have only dealt with three. There are I know of three other proofs. One using the reduced product theorem, that is probably by Pfefferman. The other two by Cowen. One using Cowen's lemma, which is a generalization of Koenig's lemma. And yesterday night I also did one proof where he essentially used another lemma, which is called Redow's lemma, using this combinatorial algorithm. Gives a short proof. I am not sure. It would be interesting to see that if the similar characterization theorem for compactness of normal MSTs can be obtained by generalizing each of these. So, and also investigation along similar lines for arbitrary or other more general classes of MSTs also remains for the future. And one might also consider generalizing the notion of compactness itself. Some such generalizations are available in literature. For example, one very famous one is that positive results in abstract model theory, where Professor Sheila and I think Professor Makowski, they discuss several such generalizations. And each such concept would then in turn offer itself to further generalizations of compact MSTs. So, in fact, this possibility was also hinted from the paper in which this work was motivated. It seems that with appropriate handling of technical subtleties, most of the results here can be lifted in a natural. So basically they talk about cardinality based notions of compactness. So you need to just be very careful about the cardinality and other things. So it would be interesting to see the details. And yeah, so there are also some remarks on the finiteness. So in the finite case, we have talked about so let me just go back to the slide. So here, this result holds for, this result holds for arbitrary MST. But this is not very practical. This is very not useful. So you would need more, it would be good to have more ideas. In fact, if the MST is normal, then you can replace for all alpha by for every finite subset of L, something similar happens here. But
does it give you compactness for first order logic theorem?
It would, as he asked, it would if you assume completeness, soundness and completeness.
Yeah, well,
that's a lot of work.
Otherwise,
No, that's a lot of work. But there is another thing. There is also something interesting. So every terse-fitted logic has a representation theorem in terms of Bayes relations. Now, if you assume that not the traditional compactness one, then I'm not sure whether this can give you something interesting, because the traditional Bayes relation, this is very easy to prove. It's half-weight proof. And then if you get the completeness from that in a different direction, and then you can show that it is not satisfiable, then I think it will give you compactness also very easy. I mean, this possibly just occurred to me, so I think I just rush back and just check whether this actually works. But I think it is possible. It should be definitely less complicated than the traditional proof of completeness. You have to take care of a lot of things to do.
well, it's worth checking. Actually.
Yes, exactly. it's very interesting. It will be done in one page.
Yeah. It's worth. Right.
Yeah. Okay, I think I'll just. Okay, that's all for today.
Thanks a lot. Perhaps we've got
questions, maybe from the online audience. No?
I thought it was too fast.
That's not the point.
So what was the the paper that inspired this?
So there is one. I think the revised version. I would suggest the revised version. There is Internet Encyclopedia of Philology, and you just search compactness theorem in Internet Encyclopedia of Philology. So.
But I was pretty sure you were referring to some
paper, yes. But the paper was earlier. The revised version is presented in Internet Encyclopedia of Philology. The name of the paper is Proofs of the Compactness Theorems, or Proofs of Compactness Theorems. I'm not sure how it is. Something like that.
Who's the author?
Alexander Prezova. I'm not sure if I'm pronouncing the name correctly, but the spelling is P-A-S-C-A-E. C-A-E, I think. P-A-S-C-A-E. Yes.
Okay, like some literature you could recommend on the topic.
You can go to read our paper, of course. That is one thing that I can definitely recommend. Shameless shelf promotion, but yeah.
Yes, and look for the references.
Yes, there. So it's available in archive. The title is same as the title from the talk.
So I have some questions, actually, and comments maybe.
Yes.
At the beginning, you were saying that the first notion of formal proof was given by some person which 1920s.
1920, yes, I think.
Yes, but it seems that really the first idea of that was